Hi, everyone, and welcome to the second talk on private information retrieval, which will be given by Dima. Dima, the stage is yours.
Thank you, Karmit, and welcome back, everybody. So before the break, we started talking about the problem of reducing the amount of computation that servers have to do in private information retrieval. And specifically, we talked about two classic approaches for this to solve this problem, namely batch PIR and PIR with preprocessing. And then we just started talking about a more recent approach called offline-online PIR. And in this hour, we'll focus mostly on this new approach of offline-online PIR. And I just want to mention that this part of the talk is based on joint work together with my co-authors, Henry Corrigan-Gibbs and Alexandra Hensinger. Cool. So just to remind everybody of the offline-online model, we said that PIR schemes in this model consist of two phases. The first phase is an offline phase in which the client obtains some piece of information about the database that we call the hint. And even though this phase takes linear time to run, the big benefit is that we only have to run it once per client, and then the client can use this hint to run many queries to the server while only paying a sublinear cost for each query. And we're going to start this hour by seeing this a construction of a two-server scheme in this offline-online model, which will have square root n communication and square root n online time. So, okay, let's get into that. So in the protocol begins in the offline phase. Here, the client chooses m random subsets of the universe of indices from 1 to n, where the size of each subset is going to be square root of n. And then the client will send the description of these subsets to one of the servers, to the left server. The left server then computes this hint bit by bit, where the jth hint bit is the parity of the database bit indexed by the jth set. So overall, there were m sets, now there are m hint bits, and the server sends back those m hint bits back to the client. And the client then stores as its hint those m sets, the description of the sets, and the m hint bits, which are parities of database records. Now, to do an actual read in the online phase, the client gets an input I, which is the element that it wants to read. And the first thing that the client does is search through its local connection of sets to find a set that contains index I. If none of the sets contain index I, then the client fails, and we'll account for those failures later on. Otherwise, the client finds a set Sj that contains I, and roughly speaking, what the client does, it punctures this set Sj by removing index I from it and sending this slightly smaller set S prime that now has square root n minus 1 elements to the right server. And the right server behaves pretty similar to what the left server has done. It computes the parity bits, the parity of the database bits indexed by this punctured set S prime and sends the bit back to the client. And now the client outputs the XOR, the somewhat 2 of the jth hint bit and the response from the right server. And notice that the jth hint bit is the parity of the database records indexed by the set Sj, and the response A is the parity of exactly the same set of bits, except bit number I is missing. So if you sum everything up, everything cancels out except X sub I, which is the correct output. So this is a rough description, but it's not quite right. The problem is that as presented, this is not secure. And this set S prime leaks a tiny bit of information to the right server. Specifically, the right server knows that as described, the set S prime never contains index I. So it can kind of make an educated guess that I is one of the elements not in the set S prime, and this violates security. So to fix that, what we'll do is we'll make the set S prime to look uniformly random. Specifically, what the client will toss a coin, and with probability square root n minus 1 over n, so roughly 1 over square root of n, it will actually send a random set S prime that will contain index I. And in the remaining probability, the much larger probability of roughly 1 minus 1 over square root of n, it will be just in the sketch. So we'll just puncture the set, remove index I, and send that to the right server. And in this case, correctness will still hold, as we see here on the screen. So let's now see what did we lose and how we fix that by introducing this this coin toss. So there are two failure events that can happen and prevent the client from correctly recovering the bit of interest. The first failure event is that if this local collection of sets does not include index I, so the client cannot proceed, it doesn't have a suitable set. But to make things work, what we do is that we choose the number of sets to be about lambda times square root of n, where lambda is the security parameter. And if we choose in a number of sets this way, then the probability that this collection of m sets does not cover the entire universe of indices is negligible in the security parameter in lambda, so we only get the negligible failure probability. Then we have the second failure event, which comes from the fact that this correctness equation that we've seen, that everything cancels out except xi, basically this equation only holds if you didn't if the coin didn't come up heads and you didn't send like just a random unrelated set. So this introduces a failure probability of about 1 over square root of n, which is non-negligible. So we can't live with that. But what we'll do is we can repeat the online phase lambda times, in some sense obliviously. So it's not like if the first attempt works, we don't continue. We have to do it obliviously, lambda repetitions. And as long as one of those iterations succeeds, then the client can recover the bit of interest. Because notice that the client knows whether an iteration succeeds or not. Right? If depending on the coin toss, the client knows whether it's just like a dummy attempt or it's a real attempt that will result in the correct answer. And as long as one of those succeeds, the client is good to go. And this introduces a factor of lambda, multiplicative factor of lambda at the cost of the online phase. So it's a little bit annoying that we pay another factor. In practice could be over 100. But in fact, in our paper, if we do something slightly more complicated, that we can avoid this blow up in the online phase, and we can achieve perfect correctness in the online phase. So we'll still have, this negligible failure probability from the offline phase, but the online phase will always succeed. And it's very similar ideas. I invite you to look at the paper if you're interested how to improve that. Okay, so let's now analyze security, make sure that the scheme we constructed is secure. So security against the left server trivially holds. The left server just sees a random collection of sets. They have nothing to do with the secret input, so there's no problem here. And then in the right server, the way that we fixed this coin toss exactly takes care of the security. And to see a sketch of the argument, notice that what we claim is that the set S prime is now a uniformly random set of size square root n minus 1, a uniformly random subset of the universe of indices from 1 to n. And again, this is not a proof, but just to convince yourself, let's look at the event of whether the set S prime contains index I. The way we structured it is that it will contain index I with probability square root n minus 1 over n, and with the remaining probability, it will not contain I. And note that this is exactly what you would expect of a random set of size square root n minus 1 to contain any fixed index. So at least with respect to, including or not including I, this thing looks random. Obviously, you need to analyze the entire distribution, but that's the argument. Okay, that was security. And now in terms of efficiency, let's do the bookkeeping. So in the offline phase, the client sends a description of lambda times square root n sets. And naively, this would be too expensive because the size of each set is square root of n, and this would already be like super linear and would beat our purpose. But what we notice is that all these sets are essentially, they need to be random set, but if they might as well be pseudo-random set, and we can just compress them using pseudo-randomness, in which case the client would just send a seed to a PRG to the left server, and then the left server would expand the PRG to generate, to run the sampling procedure and generate the description of the sets. And this would save us on, an offline communication. And then on the download direction, still in the offline phase, the server just needs to send lambda times square root n bits. So the offline communication is, roughly square root of n. Then in the online phase, the client just sends a single set of size square root n minus 1, and it gets back a single bit. So the communication here is also order square root of n. In terms of the server time, well, in the offline phase, the left server needs to process the entire collection. there are lambda square root n of sets, each of them size square root of n. So overall, we get like a quasi-linear offline time for the server. And then in the online phase, the server just needs to process a single set. So we get roughly square root n running time. So that's the basic two server scheme. There are several extensions that you can be used to either improve the scheme or achieve different trade-offs. So first of all, we chose the size of each set, such that there are square root n sets, and each set is of size square root of n. This balances communication and online time, and indeed we got both of them to be square root of n. But if we care more, for communication or more for time, we can play with the set size and achieve different trade-offs. Second, and I think someone asked about it in the previous hour, there's actually a statistical security variant. So by using a different representation of a set, instead of this PRG seed that we need to send, if we don't want to use computational assumptions, we just want statistical security, then we can work with a different description of sets, and then we would get slightly worse communication and client time, but we would not require any computational assumptions. And then finally, so as described, the scheme has square root n communication in both the offline and the online phase. And we can actually decrease the amount of communication in the online phase by somehow compressing the description of the single set that the client needs to send in the online phase. And we do this using a new primitive called puncturable sets that allow us to, on the one hand, have those pseudo-random sets, but on the other hand, being able to puncture them, remove elements while still keeping the description succinct. And with this tool, we can get logarithmic communication in the online phase. So this is much closer to what you can get, in the normal PIR setting. There is a caveat, it's that the client storage and the time grow to n to the 5/6. So we will kind of save on communication, save on server time, but the client pays more costs. And actually, there's a more recent work that showed how to avoid this blow up. So get back to square root n client storage and time with logarithmic online communication using a primitive called privately punctual PRFs that you can construct from lattice assumptions. So this is concretely, not super efficient yet, but this is a very interesting direction to trying to get everything, all the parameters of the scheme as tight as they can be. Cool. Any questions on the two server construction?
No, we don't have a question, only a request. If you could maybe go a little bit slower, because okay. It seems to be rather hard to follow. So I would say please continue, but maybe a bit slower.
Sure. I'll make sure to go slower. Yes. Okay. So in any case, we'll see now a single server construction. So hopefully things will be clear. But yeah, if you have any questions on the previous constructions, then please type them on the chat, and I'm happy to go back and explain those. Cool. So in the next part, we'll see a single server offline online PIR scheme. And the scheme that we'll see will have communication and online time n to the 3/4. So this is slightly worse, but we can construct the scheme from a wide range of public key assumptions like DDH and DCR and others. And I should just mention, we won't see this today, but if you're interested, by using fully homomorphic encryption, we'll be able to, you can construct single server offline online schemes that have better communication and better online time. Okay, so let's see how should we go about constructing a single server scheme. So schematically, what we had in the two server case is an expensive offline phase that ran against the left server, and a fast online phase that another server would execute. And so, now that we want a single server scheme, well, what we can try to do, we can say, let's try and just run both offline and online phases on the same server. The problem is that if we do this, then the security assumption would break, right? Because the two server PIR assumes that the two servers not colluding, like the adversary either sees the queries to the left server or the queries to the right server. And if we just run everything on the same server, security would no longer hold. Well, what can we do? let's try and encrypt the queries. Sorry, there's a sleep. So let's try and encrypt the queries in the offline phase, and make sure that that server will not be able to see one of the offline queries, and this would hopefully allow us to recover security. And we have two options. We will use, we will encrypt the queries with homomorphic encryption. We've already seen how homomorphic encryption is helpful in single server PIR in the standard non-offline online setting, and it will help us here as well. And we have two options. One is the heavier tool, as I mentioned, fully homomorphic encryption. We'll just encrypt the queries with FHE, and then in the offline phase, the server will just evaluate its answer function, the circuit of the answer function on the encryption of the query, and return the response, and the client will decrypt it. That works. But obviously FHE is quite a heavy hammer. And the other option, we'll try to use lighter weight tools. We'll use additively homomorphic encryption or linearly homomorphic encryption. And this would, as we'll see in a bit, this will need to work a little bit harder, and the result won't be as tight asymptotically, but we won't need to use FHE. Cool. So let's see how should we make the scheme work with linearly homomorphic encryption. And the main challenges here is that linearly homomorphic encryption only allows us to evaluate linear functions on the encrypted input. So if the answer function to the server needs to run, if it would have been linear, then we could just encrypt the query with linear homomorphic encryption and have the server evaluate. The problem that if you go back and see how the answer function works, it needs to compute parities of different bits it reads from the database, like look at sets. This is not exactly a linear function. And so what we'll do now is we'll restructure the offline answer algorithm such that it would be linear, and then once it's linear, if the inputs will be encrypted using linear homomorphic encryption, we can homomorphically evaluate the answer function and get the output. So specifically, what did we have in our offline phase? And this is like a good opportunity to review the two server scheme as well. In the offline phase, the client sends square root n sets of size square root n each, and the server needs to respond with a parity of each set. And we need to, as we said, we need to make this thing linear. The way that we'll do it is that we'll have the client send the characteristic vectors of each, of all the sets, where I wrote it down here below, a characteristic vector of a set of indices from 1 to n. This is just a vector of length n, which has 1 in every position, such if this position is in the set, and 0 otherwise. So it sends the description of overall. This will be like something like square root n sets. So the client will send square root n characteristic vectors. And then if we have this representation of the sets, what the server can do is basically compute the response as a matrix vector product between the database represented, between the database represented this time as a vector and a matrix that contains all those characteristic sets. So let's see how it works. We have one row in the matrix for each set. This is the characteristic vector, and we have the database. As a vector, and then if you do this matrix vector product, then each element in the result, it's just it's the parity of the database bits indexed by the set represented as a characteristic vector. Yeah, so this is just a way. What we've did here is we found a representation of the input. So instead of just sending the sets explicitly as a list of indices, we've represented them as vectors. And what we've gained is now that the server can compute its response as a linear function of the input. Yeah, that was our goal. And now we can encrypt this query using linearly homomorphic encryption. So what we'll do is we'll encrypt this matrix, or this, each of those vectors, that we'll encrypt each of their elements using linearly homomorphic encryption. And now the server can do this. You remember linearly homomorphic encryption allows us to do like linear algebra over ciphertext. So we get an encryption of this response vector. Again, it's encrypted index element by element. Then when the client gets the response, it decrypts every element in the vector, and what it finds there, it's just the hint bits, right? It's the hint that this response is exactly the hint bits, one per each set that the client sent. And this is kind of a different representation, but the result is the same. We got this collection of sets and their parity bits. So the nice thing about it is now the online phase can remain unchanged. In particular, we don't need to encrypt and use this linearly homomorphic encryption in the online phase, because we only need to hide the offline process from the single server. So we encrypted that. We're keeping the online phase the same. And since the offline phase is just restructured, but gives us the same output, we can then run the online phase just as in the two server case. Yeah. Any questions on that? Maybe.
Yeah. So we have two questions around slide 53, 54. I think the first you already covered in your last sentences. So it asks why encrypting or linearizing the query of the offline phase and not of the online phase.
Yeah, that's a good question. So I kind of, you could say I explained why one of them is sufficient, but you can ask like why do one versus the other? And the thing is that the reason it would have been trickier to do it with the online phase is that basically we would, so okay, the short answer is this would have prevented us from having a sublinear online phase. And the reason that in the online phase, we would have needed not only hide, like we would need to hide which elements does the server needs to access to respond to the query. And if we basically we would still need to have the server touch every possible element and run in linear time. Because, and you can say, in both in the offline phase, we already kind of pay the price of linear cost. So it doesn't, cost us more to encrypt everything with linear homomorphic encryption and have the server touch every bit of the database as it responds. In the online phase, the entire thing is that we don't want the server to touch every element, but this would somehow contradict with security.
Okay, the second question is one of the guarantees of the puncturable sets that it hides the size of the set, at least between square root n and square root n minus 1?
That's a good question. So it doesn't, but in fact, we don't need this. We don't need this property. The thing is that even in the two server case, we don't need to hide from the server the fact that it is now, it is the right server or it's the left server, like which role in the scheme it takes. We only need to hide which elements were removed from the set, and this the punctuable set takes care of.
All right, we just got a third question, which I will read out. So if we had a two-server online-offline peer with linear online queries, can you send the offline queries in the clear and the online encrypted? As this would give you a different trade-off in efficiency and would be better for a small number of queries.
Yeah, that's a good point. I think if you're willing to pay the price of a linear time in the online phase, and you're willing to pay the price of linearly homomorphic encryption in the online phase, then I think you're kind of better off just using a standard single server PIR scheme, the one that we've seen in the previous hour, which had exactly this kind of trade-off, right? It had it required linear time, it used linear homomorphic encryption, but it didn't require an offline phase. So I think in this regime, which is definitely could be interesting, you could use like the more classic schemes.
All right, that were all questions.
Fantastic, yeah. Thanks so much for the questions. It's very fun, even though we don't see each other and it's all on Zoom. The questions kind of keep it interactive, so please keep them coming. Okay, so let's maybe look at let's just analyze the efficiency of the scheme that we got. So as described in the offline phase, the client needs to actually, there was something a little bit fishy going on here, is that as described, the client needs to upload a matrix of size square root n times n, which means it needs to send n to the 3/2 ciphertext. And this is, this is very, very annoying, because you could say, if we're paying such a high price in terms of communication, like why use PIR? Why not just download everything in linear time? It seems it kind of beats the purpose. The other, we'll see how to take care of it. And then just note that in the other direction, in the download direction, the offline phase is much more efficient. You only need to download square root and ciphertext, just as in the 2-server case. And in fact, here comes an interesting idea that is very useful whenever you're dealing with PIR protocol, called rebalancing. And this dates back all the way to original PIR paper. And the idea is that if you have a PIR scheme in which the communication in both directions, so from client to server and from server to client, is unbalanced, like here, for instance, you upload much more than you download, you can rebalance the scheme and pay a little bit higher cost on the download, but gain on the download cost. The idea here is, this is, it's a little bit similar to some of the things that we've seen in the previous hour. What we can do is, instead of viewing the database as an array of bits, like an n-bit array, we'll view it as a database of square root n blocks, size square root n. And this basically shrinks the number of database, actually, which is, it's not to the 3/2, but just, square root n to the 3/2. So we would have a sublinear in n cost. This kind of rebalancing, so instead of getting a high upload, superlinear upload, and square root n download, we kind of even things out. And this gets us n to the 3/4 communication. And this idea of rebalancing is very useful in many PIR protocols, because it's often much simpler to think about a protocol that maybe has a high upload cost, and then you do apply this general technique and gain and balance things. And so this gets us n to the 3/4, like with more tricks. A little bit a different representation of the sets. You can reduce this even further and get into the 2/3 communication and a better online time. And again, the details are in the paper, but the main idea is as we've seen now. Okay, so maybe if are there any questions on this part?
No new questions.
Okay, fantastic. So let's see where we're at. So far, we've seen an offline-online scheme in the 2-server case, and an offline-online scheme in the in the 2-server case and in the single-server case. But there's actually been something that I brushed under the rug and actually requires a little bit more care. And specifically, the way that I described is I showed you how to run the online phase once, how to query a single item from the database. But part of what I've promised you is that we'll get all the efficiency benefits by being able to run the online phase many times without having to repeat the offline phase. But if we, and the naive approach could be, well, I showed you how to run the online phase once. Let's just run it more times. Not rerun the offline phase, to keep going as we started. But this doesn't work, and the reason is that if we go back to the scheme that has this collection of sets. And the client keeps, we cannot just continue running the scheme and reuse the same sets after we used one of these sets. So the problem is that once we use the particular set, we must never use it again for another query to the server. Because if we do, then we'll have a security problem. What will the problem be? Like, imagine that I use the same set SJ for 2 different queries. And each time, I was after a different index, I remove different indices. What the right server will see, it will see almost an identical version of the set. Only, on the first time, one element was removed, and in the other case, a different element was removed. So it kind of computes the symmetric difference between the 2 sets, will leak exactly the indices that the client has been trying to read. So the lesson is we cannot use the same set more than once. After we use a set, we must discard it. But now we run into a problem. Well, what happens now? That the invariant of having this collection of sets no longer holds. And the basic lesson is that we need to do something. We cannot just continue ignoring the problem. And there are several approaches that we have for allowing these multiple queries, again, to allow us to run the online phase many times without having to rerun the offline phase. And I'll present here a kind of a generic approach that doesn't use any particular details of the schemes. And this uses ideas from batch PIR that we've seen in the previous hour. I'll just say that this approach does not result in like the best scheme in terms of efficiency. And if you actually use like non-generic approaches, then you can do better. But the nice thing about it is that the same approach as I'll present here works both in the 2-server case and in the single server case. Yeah, so that's what we'll see now. Okay, so you should kind of recognize the theme here. It's similar to the batch PIR ideas that we've seen in the previous hour. What we'll do is we'll partition, we'll have the server and the client partition the database into Q random buckets. And again, each size of the bucket should be about N over Q. And what we'll do is we'll have the client and the server run the offline phase lambda times for each bucket. So in the offline phase, basically, the client will run an overall number of lambda times Q instances of the offline phase, but the size of each instance will be a much smaller database than N over Q. Okay, yeah, so that's kind of just, you imagine that you have those Q buckets, then you run the offline phase on this bucket once and then twice, like lambda times, and then lambda times on the second, and so on and so forth. The result, remember, the offline phase gives the client back a hint, and each instance will give a different hint. Overall, we'll have lambda hints for each bucket, which the client will store. And as before, we assume that both the client and the server have access to some common random partition of the database, whether it's based on some hash function or random oracle or something like that. Yeah, that's the offline phase. And now let's see how we can use that to run the online phase. And in particular, we'll see how to run up to Q different queries, up to Q instances of the online phase. So and notice that what will be different here than what we've seen in batch PIR is that now those indices can come one by one. It's not a single batch of Q queries that we need to handle. We will be able, we'll get something stronger. We'll be able to handle them one by one. Let's see how. So once the client gets a particular index that it wants to read, first of all, it finds, okay, there's a little bit like an overload. The I here appears twice, but just imagine it basically knows that this index of interest is in bucket number I and it's item number J. Yeah, this the client can know just looking at the random partition of the sets. And the client also finds like one of the hints for that bucket that hasn't been used so far. So each hint will be used only once, but hopefully there will be one that's still unused for that set. And now the client will use this unused hint HI to query its index of interest within the bucket, and will send it to the server. And it's just like either the right server in the 2-server case or to the only server in the single server case. And what the server does, it now runs the answer algorithm on the client's query for each of the buckets. So the client knows it only cares about bucket I, but the server doesn't know what I is. So the server just runs that same answer algorithm with respect to each of the bucket, gets back Q answers, and sends them back to the client. And now the client says, well, I only care about bucket number I. I'll just discard all the other answers. I'll take answer I, run the reconstruct procedure, and feed also this hint that it used. And this will give the client back its value of its bit of interest. Yeah, that's the idea. And then the last part, the client, after it used the hint, it will mark the hint is used. It will no longer use it again. And this is, this is what we'll use here, is that our base scheme is good just for a single query. So it's kind of disposable scheme. You run the offline phase and then you use it once for the online phase, and then you dispose it and you never use it again. But hopefully you have, enough hints to complete a sequence of Q queries. That's the idea. So let's see the analysis and see that everything's correct, and also did we get the right result in terms of efficiency. So in terms of correctness, this is very similar to how batch PIR originally works. The key observation here is that if you fix a sequence of Q input indices and the partition of the database is random, then the probability that you'll need to use the same bucket more than lambda times will be negligible in lambda. And as long as there's no overflows, as long as you don't run of those hints, those disposable hints, then correctness follows just from base PIRs, from the correctness of the base PIR scheme. And then in terms of security, what does the server see each time the client queries? It sees a single PIR query of the base scheme. And even though it doesn't know, that query doesn't leak which bucket the client cares about. And so the security just follows from the security of the base PIR scheme. Yeah. And okay, now let's see that we didn't lose the sublinear online time property that we wanted to. So let's just look. We can analyze the communication as well, but let's just look at the online server time. So the online server time of the new scheme T prime on a database of size n consists of the server running the answer algorithm Q times, but each time on a smaller database of size n over Q, the size of each bucket. And so if we plug in our square root n scheme and we choose Q to be cube root of n, then we plug everything here. So we get basically that the online time of the resulting scheme is n to the 2 over 3. And here you might ask, well, what happens if I want to run more than cube root of n schemes? In this case, what you'll do, you'll just rerun the offline phase from scratch. And know that it exactly balances out that the offline phase, its cost is linear, but you only need to run it once every cube root of n queries. And so if you amortize that linear cost, you get that the amortized offline cost per query is n to the 2 over 3, just as the online cost. And so everything you can run it as many times as you want, rerunning the offline phase every cube root of n queries, then proceeding with that offline phase for cube root of n queries, and the entire the server time, the amortized server time per query is n to the 2 over 3. So we get that sublinear property that we want. And as I mentioned, this is like using the black box approach. If you do a different non-generic approach, we can get square root of n without any additional assumptions, just using PRGs. And if we look at the single server case, then you remember that when we finished the description of the single server scheme, I said that if we work hard enough, we get a single query, single server scheme that has time n to the 2 over 3. And here again, if we set the parameter q, the amount of queries per offline phase, to be fourth root of n, then we'll get that the online time is n to the 3 over 4. So again, this is a transformation that takes us from a single query offline-online scheme, either in the two server case or in the single server case, into a multi-query scheme. Any questions about that, about this transformation?
No, but we have a question about the efficiency. So the question is, how concretely efficient is your single server scheme when you use FHE, and is it usable?
Yeah, that's a good question. So actually, we did not, I will talk about implementation and evaluation a little bit in the remaining time. And so our two server scheme is actually quite practical. The single server case, we didn't try. My guess is it's not quite there. So I think even the linear, even the one from linearly homomorphic encryption, the constants will be high, and I think the FHE as well. So I think, if we didn't try out, but my guess it's not quite fully practical yet.
Okay, no more questions.
Great. Yeah. Okay. The next thing I want to talk about is how to handle database updates. So it's also something that someone asked in the previous hour, like what happens if the database changes? And first of all, I want to say that this question doesn't arise for normal PIR without pre-processing, without offline phase. The reason is that if you have standard PIR and you want to change the database, everything just works in the sense that you just there's no persistent state on either the client and the server. The server just, with standard PIR, the server just holds the database in its original form. So if you need to change the database, no problem. The server changes the database, and then the next time a query comes in, it just uses the latest copy of the database to answer its query. So no real special attention needed. And for schemes that do some sort of pre-processing, whether it's PIR with pre-processing like we talked, or offline-online scheme, Well, now the client has some state. In this case, the client has some state that depends on the contents of the database. And you risk that if the database changes, then the hint and the client state, the hint and the database fall out of syncs and things might break. So the naive approach is that we can just rerun the offline phase after each change and make sure there's no like stale copies of the hint. This would work, but the amount of work for each change would be very high. It's like you need to rerun the offline phase, which takes linear time every change. And this is not super efficient. And so the refined approach that we can take is actually something, what we call kind of incremental preprocessing that would allow us to get only a logarithmic amount of server work, at least amortized, on each change. And we use here ideas that are kind of go back to work in the data structure communities of turning static data structures into dynamic data structures, and even in crypto in the ORAM literature, updatable encryption. These ideas are I think classic ideas. So again, what we'll do here is that we'll divide the database into buckets, but this time it'll be a little bit different than what we've seen before. And we'll update those buckets using two rules. The first rule is that whenever you insert a new record into the database, it'll get its own bucket. And then the second rule is if you have two buckets of the same size, you merge them and double the size of the bucket. So for now, imagine that the only changes that we support are additions, but you can adjust it to handle like deletions and modifications. So every time a new record is added, the server creates another bucket, then maybe another record comes in, another bucket, two of them are of the same size, so you merge them. And you keep going like that until basically forever, as long as you're managing your database. And the observation here is that because those buckets, because of this merging rule, at each point in time, we'll have at most a logarithmic number of buckets. Yeah, so because we just double the size every time, and there's at most one of each size. So let's see how to use it. What we'll do now is that in the offline phase, the client will obtain a hint for each bucket. Right, so we have buckets of different size, and the client holds a hint. And when a new bucket is created, the client and the server run the offline phase only on the new bucket. So you don't need to repeat the offline phase from scratch. You just run it on a new bucket, and you get like the delta, the new hint. And the idea here is that now we only have a logarithmic overhead in terms of by handling updates compared to a database without updates. The reason here is that every record is only preprocessed at most once in each bucket. So you kind of, every record as it travels between the different bucket sizes, it gets preprocessed multiple times, but at most log n time. So it's not like for every bucket you need to rerun the entire preprocessing. You only get a logarithmic overhead overall. And then in the online phase, when the client wants to read a particular index, then first of all, it maps it into the right bucket that it knows the structure of the sizes of the buckets. It knows which bucket that the input falls into. And then it sends a query, an offline, like the query of the offline online scheme with respect to that bucket. And again, to hide the size, which bucket it is interested, it can also send queries like dummy queries for the remaining buckets. And the server answers all of these queries, sends back the responses, and the client can recover the value from the relevant response. And here, actually, because the sizes of the buckets are like exponentially decreasing, if you do the math, then it turns out that the overhead that you get from having those log n buckets is actually only multiplicative constant because the sizes are decreasing. And so we paid only multiplicative constant in the online server time by allowing updates as compared to just the static database case which we started with. Yeah. Any questions on that?
Yeah, so regarding the updates, we have a question. If it means that the client obtains all the history of XI if XI was updated.
That depends. I think naively we could say the way that we described, we only described additions. So you can imagine like things. You in this sense you can maybe think of it of getting the full history. Recall that in this setting, we don't really have any privacy requirements for the server, so we don't really care about those, but you can imagine somehow adjusting things to take care of it. Yeah, we could. I think even those OPRF ideas that we mentioned, I think you could actually use them if you care about like deleting history or something like that. It's a good, interesting question.
And a second question from a few slides back. Would it maybe be possible to use the answers for the other buckets, maybe together with the hints already there, to generate new hints?
Yeah, that's actually, so I'm not sure if this was meant by the question, but I think it's a very good point. In fact, if you recall, I mentioned this non-generic approach to handle multiple queries, and it actually uses ideas of that same, of exactly that type. So, from even without, updates, there is a way of actually updating the hint from the answers. And this is something that we do to get a non-generic approach. So I think that's a clever idea, whoever suggested it. Yeah.
Okay, that were all questions.
Great. Okay, and I should mention then, if we don't like the logarithmic factor, there's actually an upcoming paper from, I think, Sebastian Angel's group that develops more efficient incremental offline-online PIR. I think it's going to be in Usenix this summer. Okay. Okay, actually, let me, I want to mention the lower bound. I might skip the proof because I want to talk a little bit about implementation. But I should just mention, I kind of said it before, but we can actually show that in some respect, our schemes are optimal. And specifically, we show that every offline-online PIR scheme in which the server stored the database in its original form, and it uses, C bits of communication and online time T, it must have the product of the two must be, at least linear or quasi-linear. And this shows us that the square root n schemes are in some sense efficient. I wanna emphasize that there is hope that by maybe combining some ideas from PIR with preprocessing, in which the servers encode the database and don't store it just in its plain original form, like the lower bound doesn't capture that. So maybe this is something worth looking for in order to improve on this. Cool. So that's the lower bound. I will keep talking a little bit about the lower bound proof, and it's in the slide, so I think you can look at it. But I want to talk a little bit about evaluating PIR, and specifically, let's put offline-online PIR to the test. So one thing that together with Henry we've done is we've actually built a system that uses PIR for something called safe browsing. And then we integrate, I'll explain what it is, but we basically build the system. We integrated it with a Firefox browser. And we wanted to see, how does offline-online PIR compares with more traditional, DPF-based PIR, in the plain setting, not in the offline-online setting. So you might recognize the screen that you get in Chrome or in Firefox that warns you of that you're about to visit a dangerous website. It could be something that's used for phishing or for spreading malware. And this is based on a system called safe browsing that Google and a couple of other providers operate. And the way that the system works today is that basically Google, they crawl the web and they collect a list of dangerous URLs that they consider to be malicious for one reason or the other. And they have this database of around 3 million, or maybe by now already 4 or 5 million URLs. And they store for each URL, it's SHA to 56-bit hash, not just a hash of the URL. They do some kind of normalization, but that's essentially it. And then your browser, whether it's Firefox or Chrome, before it fetches any resource from the web, it could be a web page, a JavaScript, or whatever, it checks the hash of this URL against this remote list. So there are a little bit like caching going on the client side to avoid the client talking to the server each time, but we can kind of ignore it for now. Schematically, what happens is that basically the browser hashes the URL. It takes some short hash prefix and it talks to the server to check whether there is a full entry on the list that starts with this prefix. This is the prefix mechanism is to give a little bit of privacy which it does help. But the basic problem with safe browsing, for which we'll use PIR, is that these lookups, these safe browsing lookups, leak information about the user's browsing history to the server, to the service provider. Yeah, that's the problem. And what we want is to be able to enjoy the benefits of safe browsing and protect ourselves from dangerous websites, but not having to leak information about our history to the service provider. And this is something that we tried using PIR for. So in particular, we built a system called checklist. That it could be used for other types of these block lists, but specifically we evaluated on the safe browsing block list. We use the 2 server variant, so we need to operate 2 safe browsing servers and assume that they're non-colluding. And what we did, we implemented as part of our system, we implemented both this new offline online PIR and the standard DPF based PIR, and want to see how do they fare against the other. And the benefit of this is that now the PIR will guarantee that there's no leakage about the browser history to the service providers. So the way that we did the evaluation is that we monitor the week of safe browsing requests and responses just on our own machines, and during normal browsing activity, we looked at the responses that your browser, the request that the browser sends to the server, and specifically from these you can already deduce different parameters that help in the evaluation. Things such as the frequency of lookups, the frequency of updates to the database, everything that these things that we discussed, and as well as how big is the database, how much it grows, and then we use this recorded trace to basically evaluate with different PIR schemes. So this is what we see here is the cumulative server CPU time that our system requires. Using say here it's several months of simulated user activity based on the recorded trace, and we compare here. This is measured in seconds, and we compare here the amount of server time needed for the DPF based PIR and the offline online PIR. And what we see here is that in terms of server computation is as expected, the offline online PIR is more efficient. It's asymptotically it's square root compared to linear, and concretely because of some factors it turns out to be about factor of 5.5 requires less computation. But everything on the other side. For the client, we mentioned that the offline online PIR is more expensive, and indeed, the DPF-based PIR requires less computation for the client. So here it's the same type of graph. Only we look at client computation, and we see if you're in the setting where you care about client running time, then you probably want to go with DPF-based PIR rather than offline online PIR. And in terms of communication, then you see also that the offline online PIR comes with its cost. It requires more communication. A lot of it actually has to do with this update mechanism. This log factor adds up, and I think it contributes to a lot of this difference. So it's actually interesting. I didn't have a chance to look at it yet, but this new paper on incremental PIR might help with this, for instance. So I think kind of the conclusion of this evaluation, and I guess of my talk in general, is I think that PIR has an application to different privacy preserving systems, and we've seen now that the cost of PIR are approaching the realm of practicality. And what I wanted to show from this evaluation is that you actually have several alternatives. We don't have a single solution that's best across all parameters, but we have a menu of things we can change, whether we care more about server computation, client computation, and this kind of stuff. And but I think the interesting next challenge is to try and make these things work. So we only built a research prototype, and it's interesting to see if PIR can be helpful in other settings. So that's everything I want to talk about PIR. I'll be happy to take more questions now. I'll just say that if you wanna, the slides are on the school website. If you want to look at the offline online PIR papers, they're all linked from my webpage. And thanks for attending the talk.
Thanks. So no questions yet, but I may ask one myself. So in this safe browsing application that you mentioned, in terms of communication, how does it compare to the naive solution? I think if you have like 3 million web pages, and you probably can truncate the hashes that you send to the client a bit, so you would have a database of maybe 50 megabytes. And I think your peer schemes also required in that order of magnitude. So how do you justify then using peer instead of the naive solution?
Yeah, that's it. I think this is a very, very good point. I think so. I think we actually did the calculation. It does turn out that PIR still save you on communication compared to the naive approach of the downloading. So I think if I remember correctly, at least like a factor of 2. I think it's still more efficient than download the entire database, even if you truncate the hashes. So I think if you fix the rate of false positives that you want to have, then you think you still gain something by using PIR. But I completely agree that in this particular application, I wouldn't rule out just the naive approach. I mean, it's not. I don't think there is a benefit of using PIR. For instance, like if you would just include the entire safe browsing list, it would maybe I think more than double the size of the mobile, the APK to download the app. So it's not it's not negligible compared to the size of the application. But I think that for other applications, that's I think why I'm excited about it. I think that there are other applications where PIR could be much more helpful, and where the naive solution would be out of the question.
Okay, thanks. And maybe you can comment a bit on latency. So as a client, if I type in a URL and press enter, I want it to show up like in 10 milliseconds or so. And what if I run the peer protocol, even like the lightweight online phase, like how much does it add to the latency there?
Yeah, that's another excellent question. So first of all, like I should just mention, the offline phase, we can run it, out of band without waiting for you to click. So that's already helpful. The online phase, in our evaluation, at least like we did, from our personal devices or test devices to a cloud server, it turns out that even linear time PIR in terms of latency, just like with the memory speed today, and the entire database fits into memory. There's not really a noticeable effect on latency. So I think whether you're using DPF-based PR or offline online PR compared to the network round trip time, I think you're good and it's not noticeable. We did measure that. I think the main problem is that in terms of memory bandwidth, this is why a single server won't be. It's hard for it to process a lot of requests, and so this is what motivates using sublinear time PIR. More for the bandwidth than for the latency.
All right, thanks. I think we don't have any other questions right now.
Right. Thank you, Dima, for 2 great talks. And we will resume for the next session after the break.
Thank you. Thanks again for inviting me to the Winter School.